All right, symmetry is something that's, been discussed in the past in this course. So this is not going to be entirely new here. Now, the difference between a continuous and discrete distribution is that the random variables associated with such distributions are very different in the sense that the discrete variables can only assume a discrete number of values, but continuous variables can assume a continual infinite swath of decimal and fractional values. So that's the main difference between a continuous distribution versus discrete. We have seen with binomial discrete distribution that the distribution can be symmetric. Okay, so it's not impossible for a discrete distribution to be symmetric. In fact, many are. And this symmetry also transfers over to continuous distributions here. Okay. Now, an interesting thing occurs here as you increase your sample size. If we, for instance, have a sample of 100 women and make a histogram of their heights, you can see that the histogram, this one over here to the left, is roughly symmetric, not perfectly symmetric, but it's pretty darn close, and it's pretty close to being bell-shaped. All right. Now, as the sample size increases, what happened if we increase the sample size and we decrease the widths of the classes, we tend to have more bars, okay? And our distribution actually starts to approach more and more of a symmetric bell-shaped distribution. To the point whereby if you allow your sample size to actually approach infinity, what happens is these bars increase here and the widths of these classes decrease. All right, we're actually approach zero. And what happens is these ever increasing number of little bars with ever decreasing class widths tend to carve out a more and more symmetric bell-shaped distribution. So many continuous random variables and even some discrete variables have distributions that are close to a normal distribution. We would classify these as being approximately normal. Very rarely do you have a perfectly normal data set. But again, as your sample size increases, and we'll see that this will also be true with what are called sampling distributions of sample means, for instance, the distribution tends to become more and more normal, right, bell-shaped. All right, now the function that generates a bell-shaped curve or a normal distribution probability curve is a rather complicated function. It's not an elementary function. It is actually a base E exponential function. All right, and it is a two-parameter mathematical model, if you will, in the sense that the parameters are the mean and also the standard deviation. So for that reason, when we're talking about a normal distribution, we normally say a distribution is normally distributed. We use the letter N for the word normal, with a mean of mu and a standard deviation of lowercase sigma. Okay. Together, these two parameters basically determine the shape and location of the normal distribution bell-shaped curve in the XY plane. So notice that we do have a constant being multiplied by base E. Base E is the natural base in mathematics. It's approximately about 2.718. It's called the natural base. It is an irrational number in the sense that this decimal rambles on forever, never terminating or never repeating. So we do have a constant, which involves the standard deviation of our data, times base E raised to this rather complicated exponent here. We have -1/2 times the square differences of the data observations and the mean of the data set divided by the variance of the data set. So if you were to graph this function, y versus x, you would get, for some values of the standard deviation, lowercase sigma, and mean mu, you would generate a normal curve here, or a bell-shaped curve. Okay. Now the parameter mu, the mean of the distribution, basically locates where the bell-shaped curve appears in the xy plane. For instance, if you look at this diagram to the right here, a normal distribution with a mean of 0 would be further to the left on the x-axis or in the plane compared to a normal distribution with a mean of 2. All right. So the mean basically just determines where on the x-axis the normal distribution sets up. The second parameter, the standard deviation of the data set, determines how wide or how narrow your normal distribution is. The larger your standard deviation, the wider your normal distribution or bell-shaped curve is, to reflect the fact that your data points are more dispersed about the mean, median, and mode. If your standard deviation, lowercase sigma, is very small, that indicates your data values tend to cluster up very closely around the mean, median, and mode, and therefore your bell-shaped curve will be much more narrow. Okay. So the mean locates the normal distribution in the plane, and the standard deviation basically determines the shape of the normal distribution, how narrow it is versus how wide or splayed out it is. Okay, now these are all properties that normal distributions obey or enjoy. All normal distributions are bell-shaped. All right. So therefore, like, the highest point of the bell-shaped curve or graph occurs in the middle and drops off with equal frequency to the left and to the right of that point. Right. The mean, median, mode are all equal and all located at the center of the distribution. So the mean, median, and mode would be this value right here. A normal distribution curve is unimodal, which means it only has one mode. The curve or the graph is symmetric about the mean, which means the graph drops off with equal frequency to the left and to the right of the mean, median, or mode. The curve is continuous, as the normal distribution is a continuous distribution, and therefore its random variable basically involves working with intervals on the x-axis. The curve, we say, is asymptotic with respect to the x-axis, in the sense that the graph never touches the x-axis, although it does get closer and closer and closer to the x-axis as we move in the negative infinity direction or the positive infinity direction. You can see that the curve is getting closer to the x-axis, but will never touch or cross the x-axis. Because of that, we call the x-axis a horizontal asymptote to the graph of a normal probability distribution curve. This is very important. The total area under the curve and above the x-axis is 1 or 100%. So what we're going to learn very quickly here, ladies and gentlemen, is that for continuous probability distributions, it's the area between the curve and the x-axis, which are called probabilities. Okay, so areas are equal to probabilities with continuous distributions. All right. So if you take the area of the entire normal distribution curve from negative infinity all the way to positive infinity, that area would sum up to 1 or 100%. We've seen that that was also the case for a discrete distribution when we looked at the sum of the probabilities for all the outcomes of such a distribution. They must also sum up to 1 to be a valid distribution. Well, that's also true with continuous distributions. But now we speak in terms of area between a curve and the x-axis. Okay. All right. Now, the area under the part of the normal curve that lies within one standard deviation of the mean is about 68% of the entire area, in accordance with the empirical rule. Do you remember what the empirical rule said that we investigated in the past when looking at measures of dispersion? The empirical rule says that if we venture one standard deviation either side of the mean, okay, so from one standard deviation below the mean to one standard deviation above the mean, we will have encompassed about 68% of our data. Well, geometrically speaking, that's saying that about 68% of the entire area of this normal curve lies within that interval from one standard deviation below to one standard deviation above the mean. By the time you venture two standard deviations either side of your mean, obviously you're encompassing more of your data. And according to the empirical rule, about 95% of your data points have been accounted for. For that reason, on the interval from two standard deviations below the mean to two standard deviations above the mean, that accounts for 95% of the area of the entire normal distribution curve. And by the time you venture three standard deviations either side of your mean, you're basically encompassing about 99.9% or 99.7%, depends on what textbook you look at. About 99% of the area of the entire curve lies three standard deviations below your mean to three standard deviations above your mean in this much larger interval here, okay? So we can see that the areas underneath this normal distribution curve cooperate with the empirical rule that we touched base with in the past. And notice we have perfect symmetry here with this normal distribution curve. If 68% of your data lies between one standard deviation below to one standard deviation above your mean, then we would expect about half that, or 34% of your data, or 34% of the area of this curve to lie from the mean up to one standard deviation above the mean. And also we would expect about 34% of the area of this curve to lie from the mean to one standard deviation below the mean. So we have perfect symmetry with the normal distribution. And that makes this distribution very easy to work with when computing probabilities, is this wonderful symmetry that exists. All right, so when you have a data set, a continuous data set that is bell-shaped and normally distributed, we call that a symmetric distribution. And we also can say with certainty that the mean, median, and mode are equivalent to each other. And the distribution, of course, is unimodal. However, if you look at this diagram in the middle here, such a continuous distribution as this would be negatively skewed or skewed to the left, in the sense that the graph tails off more gradually to the left of the center as opposed to the right where there's an abrupt drop. In this case, the mean would be less than the median, which would be less than the mode. So it's important to note that. The median value is in between the mean and the mode. The mode is the value furthest to right on the x-axis, and the mean would be the value furthest to the left on the x-axis. If your continuous distribution is positively skewed or skewed to the right, as this bottom graph indicates, then the mode would be the value furthest to the left on the x-axis. The mode would be greater than the median, which would be greater than the mean. All right. Notice the mean is the statistic that is the most susceptible and most influenced by what are called outliers. Outliers cause your data set to be skewed. So if your data set is plagued with outliers, that's greatly going to affect the mean. And for that reason, the mean is not really a good measure of central tendency when your data set has outliers in it. You should be using the median as opposed to the mean in that set of circumstances. Okay. All right. This is a normal distribution, and ladies and gentlemen, the most important normal distribution, because there are an infinite number of normal distributions. Because remember I said a normal distribution is a two-parameter model. Well, since the mean could be any value, the standard deviation could be any value, there's really an infinite number of normal distributions. Probably the most important one that is used or studied is called the standard normal probability distribution. The standard normal probability distribution always has the mean being equal to 0, and the standard deviation is always equal to 1. That's always true for a standard normal probability distribution. Now, this standard normal distribution is important still in our work today, but it was even more important yesterday before we had our calculator. Before we had our TI-84 calculator, ladies and gentlemen, in order to compute probabilities underneath any normal distributions curve, we had to first of all standardize the observations to conform to the standard normal distribution, because we only had tables for the standard normal distributions areas underneath the curve. We did not have tables for all other normal distributions. In order to be able to use those tables, we had to first of all standardize our data values to conform to the standard normal distribution. That's not really, a large issue today in light of the fact that we do have the wonderful TI-84 calculator that can basically compute probabilities for any normal distribution, not just the standard normal distribution. So that kind of renders the tables that we used to use in our appendix in the back of our stats book kind of obsolete, where we don't have to go back and use the normal table, or sometimes it was referred to as the Z table. Okay. But this is the function that generates the graph of the standard normal distribution, again, of which has a mean of 0 and a standard deviation of 1. All right. But like any normal distribution, the proportion of the area still obeys the empirical rule. So there's no difference. The only difference now is on the horizontal axis, we just have integers representing the number of standard deviations away from 0 we are. So again, from 1 standard deviation below to 1 standard deviation above the mean, notice the mean is 0 now. It's the standard normal distribution. 68% of your data points lie. 2 standard deviations, about 95% of your data points lie. 3 standard deviations, about 99% of the area has been accounted for, or 99% of your data points have been accounted for. We've seen this Z formula before, ladies and gentlemen. This is called a standardization formula, which enables us to take any observation from a normal distribution and to standardize it so that it conforms to the standard normal distribution. We also used this formula in the past to determine how many standard deviations away from the mean a data point is, by taking the data point, subtracting off the mean of the distribution, and dividing by the standard deviation. So we have used this formula before. We called these values Z-scores or Z values in the past. All right. And again, this formula is used to standardize any continuous random variate that is normally distributed so that it conforms to the standard normal distribution. We don't really need to do that too much nowadays, since we have the TI-84 calculator, which circumvents us having to go back and use the tables in the back of our book. So that's a good thing. We don't have to deal with that. This is basically just showing you how you would go to the back of your book and use the Z table if you want to do that. But like I said, ladies and gentlemen, if you have a TI-84 calculator, you don't need to do this because our calculator can compute normal distribution probabilities very easily without having to resort to using a table. So the tables really are kind of like obsolete in this day and age. All right. Okay. And I'm going to show you on your calculator how we're going to compute these probabilities. So just hang tight here. All right. See, in the past, we had to go through and do subtractions and all that stuff with symmetry. We don't need to do any of this later because we got our TI-84 calculator here. So. All right, this is important. I did indicate that probabilities are equal to areas. So the size of the area underneath the normal distribution is equal to the probability that a random variable will assume a value in that particular interval. Okay, for example, if we look a z-value of 1.73 up in the table or on our calculator, we will see that about 95.82% of the area of the entire curve lies below that value. All right, notice because our z-value is 1.73, that means that we are 1.73 standard deviations above the mean. And because the mean is 0, this is our standard normal distribution. This is our normal distribution where the mean is 0 and the standard deviation is 1. That's your standard normal distribution. All right, so this area you see shaded here, you know what that's equal to? It's equal to this probability. The probability that the z-value of a standard normal distribution takes on a value that's less than 1.73. This probability is equal to this shaded region here. It's equal to this area here. Okay. How would we compute this area, though? Suppose we do not have a table or a TI-84 calculator. Well, ladies and gentlemen, what you would have to do in order to get an accurate idea as to what this area is precisely is you would have to use what's called integral calculus. And you would have to integrate, okay, the normal distribution function on the interval from 1.73 down to negative infinity. You'd have to integrate that function to find the area underneath this curve. Well, this is only elementary algebra. This is not presupposing that we've had any calculus. And so we're not going to do that. We don't need to use integral calculus because to the rescue is our powerful TI-84 calculator. That calculator is going to compute this area precisely on this interval from 1.73 down to negative infinity. Okay. And I'm going to show you how to do that on your calculator now. All right. So how would we, using our calculator, compute this area? Well, what we're going to do is we're going to go grab a function on our machine, ladies and gentlemen, which is called the normal CDF function. This stands for normal cumulative distribution function. Just like we had a binom PDF and a binom CDF, all right, we have a normal CDF function. And the normal CDF function will always compute probabilities underneath a normal distribution curve, okay, within some interval. And this is the argument list for the normal CDF function to do what it does. We must always open up by indicating the lower endpoint of an interval. Lower endpoint. Comma, and then we'll have the upper endpoint of an interval on the horizontal axis. These endpoint values are always on the horizontal axis. Whether it's called the x-axis or the z-axis, doesn't matter. This will be the upper endpoint. Okay. Comma. Then we must specify the mean of the normal distribution, comma, and then the standard deviation. This is the required argument list for the normal CDF function to do its job. It's got to be in this order. Lower endpoint, comma, upper endpoint of an interval, comma, the mean of the distribution, comma, the standard deviation of the normal distribution. Now, negative infinity. Negative infinity is not a number. So how do we trick our calculator into, viewing the leftmost endpoint, should that be the case, to be negative infinity on an interval? Well, ladies and gentlemen, we use 10 to the negative 99. We use negative 10 raised to the 99th power. For all practical purposes, we call this negative infinity. That's good enough to call negative infinity, negative 10 raised to the 99th power. Positive infinity, If we go far to the right on an interval underneath the normal distribution curve, that's called the positive infinity direction. We use 10 raised to the 99th power, positive 10 raised to the 99th power to simulate positive infinity. Well, there you go. It's good enough. By the time you go all the way out here to 10 to the 99th magnitude on the x-axis, way out here to the right, this normal distribution curve has gotten so darn close to the x-axis so that any other additional area contributed is deemed as being negligible. I'm not saying there's still not any area underneath this curve, between the curve and the x-axis. When you go far, far to the right on the x-axis, there is some area, but it's very, very, very small, to the point whereby we deem it as being essentially negligible. Same reason, if you go far to the left on the x-axis, far to the left, the graph of the normal distribution curve gets closer and closer and closer to the x-axis. Now, that's not to say at negative 10 to the 99th power that there's no area between the graph of the normal distribution and the x-axis, because there is some area. It's just that it's so minusculely small that we deem it as being negligible and contributing to any more area that we wish to compute. All right. So do we have this this written down here so far? Because I got to get rid of this on the screen here. So normal CDF function, lower endpoint, comma, upper endpoint, comma, the mean of the distribution, comma, the standard deviation. All right, I'm going to show you how to compute this area or the probability of our z variate or z random variable, assuming a value that's less than 1.73. Actually, you know what? I could do that up here. We don't have to erase this. All right, so we're going to have to go and grab our normal CDF function. I'll show you where that's at in a moment on the calculator. So we're going to grab normal CDF. And ladies and gentlemen, to compute this probability, what's the left endpoint of our interval? To say z is less than 1.73, our left endpoint would be what? Well, we go to the left forever. Do you agree? So what is our left endpoint?
Negative infinity.
Negative infinity. So we type in negative 10 raised to the 99th power. Negative 10 raised to the 99th power. That's our left endpoint of this interval of interest. Comma, the upper endpoint is 1.73. Comma, the mean of this distribution, since it's the standard normal distribution, is 0. Comma, the standard deviation of this normal distribution, since it's the standard normal distribution, is 1. When you dial it up, you'll compute this area, this shaded area. You'll compute this probability. So let's go get our calculator and show ourselves how to do it. So we'll bring up the calculator. Okay. I'm going to have to kind of fit it in here. All right, ladies and gentlemen, we go to our distribution mode. So second vars takes us into distribution. And guess what? It's the second function from the top, normal CDF. That's the function we want. So we activate the normal CDF function, which again hangs out in distribution mode. So how did I get that again? Second vars, normal CDF. Hit enter. Now, some of your calculators will have this environment laid out kind of vertically, but some of your calculators will just have normal CDF with an open parenthesis waiting for you to populate the argument list. Okay. So what is my lower endpoint? That's negative 10 raised to the 99th power. You know what, ladies and gentlemen? Negative 1e99 is saying negative 10 to the 99th power. That's the same thing as negative 10 raised to the 99th power is negative 1e99, because that's saying negative 1 times 10 to the 99th power. Okay. But if you want to just type it in manually, whoops, you'll type in the negative sign, negative 10 raised to the 99th power. Hit enter. That's the same thing as negative 1e99. Upper endpoint is 1.73. Notice the default values for mu and lowercase sigma are 0 and 1. So your default normal distribution when you get into this is the standard normal distribution. Hit enter, hit enter, hit enter. See, some of your calculators have it laid out horizontally like this, where you're going to have to populate your argument list this way. Just make sure you separate your values with commas. Okay. Hit enter, ladies and gentlemen, and we'll compute that probability. It should be about 0.9582. There it is, 0.9582. So that is the area of this standard normal distribution curve that is less than z equals 1.73. That's the area, or that's the probability that your random variable z would be assigned a value of a value less than 1.73. Everybody understand how we computed that area or that probability there underneath that standard normal distribution curve? So that's about 96% of the area has been accounted for, less than 1.73. So what percent of the area, ladies and gentlemen, is above 1.73 for the standard normal distribution curve? What percent of the area would be above? About
0.5.
Yeah, about 0.5, maybe just a hair under 0.5. That would be the upper tail area, we call it. Upper tail area here. All right. Makes sense. Remember, the area underneath the entire curve from negative to positive infinity has to be what? 1. Has to be 1. Below 1.73 for the standard normal distribution, you've accounted for about 96 hundredths of that area. Okay. Any questions? How we computed the area of that shaded region underneath the standard normal distribution curve using our calculator, the normal CDF function? All right. Whoops. Sorry about that. Yeah, like I said, we don't have to use tables anymore to compute these areas. We just use our calculator. All right. Hey, let's try this one. Ladies and gentlemen, now they want you to compute the probability that z lies between 0 and 2.53. In other words, they want us to compute this shaded area underneath the curve. And again, to compute this area geometrically without using a calculator or a table, you'd have to use integral calculus. But here's the problem. Trying to integrate that base E exponential function, which basically carves out this normal curve here in the plane, that is not an elementary function, ladies and gentlemen. In fact, there is no antiderivative for that function. Because of that, you have to literally use numerical integration. And that's where the tables came into existence, is by numerically integrating this very complicated function between 0 to 2.53 on that interval. But we don't have to do any of that because we got our calculator. Now, check this out. So we're trying to compute this probability right here. And I want to point something out else that's very important here. Does it matter if you have the equal signs or not with your inequality symbols? The answer is it doesn't matter. The equal signs, whether they're thrown in with the inequalities or left out, make absolutely no difference whatsoever. I'm going to show you why. Ladies and gentlemen, whether you represent that probability like this or this, these are saying the same probabilities, same areas underneath the same curve. Okay, so you don't need to even put the equal sign as part of your inequalities. Here's why. Suppose I wanted to compute the probability that z is exactly equal to 2. Exactly equal to 2. Well, that might be right here, let's say. Let's say this is 2 on the z-axis here. But what did I say about probabilities for a continuous distribution? Probabilities are equal to what? Do we remember? For a continuous distribution, probabilities are always equal to
Area.
areas. Remember, that probabilities for a continuous distribution are equal to an area. So I have a question for you. If I want to compute the probability that z is exactly equal to 2 or exactly equal to any number, is there an area? Does this have any area to it? This line, this vertical line? There's no area. To have an area, you have to speak in terms of an interval, a lower and upper endpoint. Because there's no area, this probability is 0. Doesn't make any sense to even, consider a probability for a continuous distribution like that. That's why it doesn't matter if you have the equal sign as part of your inequalities or you leave them off. Doesn't matter, because we are speaking in terms of an interval. It's the interval that gives us the area, right? It's not whether z is equal to some value. Okay. All right, so let's try to dial this up on our calculator. So let's go get our calculator and compute this probability or this area. All right, where to put this? Got so much garbage here on my screen. Hold on. Let's see if I can erase some of this stuff here. Okay. I just put it right on here. All right, here we go. So go get the normal CDF function. So second vars gets into your distribution mode. Go grab the normal CDF function. What's my lower endpoint? My lower endpoint for computing this area here is 0, correct? Z equals 0. What's my upper endpoint? Well, my interval goes from z equals 0 to z equals 2.53. So my upper endpoint is 2.53. What's my area? What's my mean of this distribution? Well, it's still a standard normal distribution. So the mean is still 0 and the standard deviation is still 1. Hit enter. There it is. Hit enter again, and boom, you compute that area. That area is going to be about 0.4943. Or we say that's the probability that z would take on a value between 0 and 2.53. Almost a 50% chance. Okay? So that is the shaded area that you see in this picture here. In other words, that accounts for about 49% of the area of the entire curve, that shaded region there. Does this make any sense here? Our computing areas underneath the standard normal probability distribution using the normal CDF function. All right. In the old days, we actually had to go back and use our table, but our table only worked one way. It was a real hassle, so you don't need to do that anymore, right? This is just running you through the TI-84 way of computing probabilities underneath the standard normal distribution curve. All these are the standard normal distribution curves because the mean is 0 and the standard deviation is 1, correct? All right. So that's just re-emphasizing things I've already shown on your calculator. All right. Okay, let's see if we can go to our textbook and have a little bit of fun in section 6.1. All right, hold on here. All right, so I'm going to go into section 6.1. We're going to do a couple problems here. All right, so section 6.1 is entitled Normal Distributions. And like I said, if you ever get a chance to maybe just kind of browse through this section, it would be worth your while, as it will just, reconfirm what it is that I've gone over, and might actually give you a couple of other examples to play around with in here. Okay. These are things we've already seen on a PowerPoint here. Okay. All right, let's see what we got here. All right, so here's the problems. They begin right here. What are characteristics of the normal distribution? Well, there's several. Must be bell-shaped, must be symmetric about the mean. The mean, and mode are equal. It's continuous. It never touches the x-axis. We say the graph is asymptotic with respect to the x-axis. The area under the curve the area underneath the entire curve must sum up to 1. It is unimodal, only one mode. And of course, the areas within any interval with regards to standard deviations either side of the mean obey the empirical rule that we looked at or touched base with in the past. Okay, so I would like you to use your TI-84 Legon in computing some probabilities here. I'm going to have you compute a couple here. So like open up a running tab on classwork number 1. All right, I want you to do problem number 8 here first. All this is going to go on to classwork number 1, number 8. We want to find the area under the standard normal distribution curve to the left of z equals negative 0.75. If you were to draw a graph of this area, and it's always a wise thing to do so, I always recommend drawing a graph here. Here's your standard normal probability distribution. Of course, it's a bell-shaped distribution. Now, the mean is 0, so the mean is right here at 0. So where would negative 0.75 be if this is my z-axis here? Would it be to the left of 0 or to the right? Negative 0.75. It's going to be somewhere, I don't know, it's going to be pretty darn close to the mean. We'll call that about negative 0.75. And so this probability that they want you to find is really equal to the area that's to the left of negative 0.75. So they really want you, okay. They really want you to find this area here. So they want you to find that area. That's what they want you to do with this problem here. Okay, go ahead on your calculator and find that area using the normal CDF function. All right, so we're going to go grab our normal CDF function. Notice the left endpoint of this interval is going to be negative infinity, which we're going to fool the calculator into thinking it's negative 10 to the 99th power. The upper endpoint is negative 0.75. So let's go grab our calculator, and his dial is up here. Second vars, normal CDF. Lower endpoint is negative infinity, which is negative 10 raised to the 99th power. Upper endpoint is negative 0.75. The mean and standard deviation is 0, and 1, since it's the standard normal distribution. You're probably wondering, when are we going to run into other normal distributions where the mean is not 0 and the standard deviation is not 1? That's going to be in the next section when we start applying normal distributions in the real world. All right, ladies and gentlemen, hit enter. And boom, that area or that probability is about what? 0.227. Did we all get that?
Yep.
That's that area you're looking at that's shaded in red there. So that would be the area about 0.227. That accounts for about 22.7% of the area of the entire curve. What is that? That being less than a z-value of negative 0.75. Okay. All right, or we would say there's about a 22.7% chance that our z-value will be less than negative 0.75 if you were to randomly choose a z-value from negative to infinity to positive infinity. Okay. All right. Any questions how we're computing that area or that probability there? Okay. All right. That one's good. Now, ladies and gentlemen, I want you to do number 9. Just roll number 9 into classwork number 1. Compute the area to the right of z equals 0.24. Or that's saying compute the probability that z is greater than. And again, whether you want to put the equal sign or not is up to you. It doesn't matter if you do or don't put the equal sign. It doesn't matter. We're talking about an interval always with continuous distributions. Okay, so go ahead and compute this probability or find that area. And 0.24 being greater than 0 would be about right here, 0.24. So you're going to have to find this area. This is the area they want you to compute now. All right, go ahead and find that area there using your normal CDF function. Okay. Anybody get it? What area did we get there? All right, so your lower end point now is what? Positive 0.24. Upper end point is positive infinity, which we just type in positive 10 raised to the 99th power. 0 and 1 are the mean and standard deviation, still a standard normal distribution. Hit enter, and did you get that probability about 0.405? Are we getting that?
Yep.
So this is now going to be 0.405. All right. So above z equals 0.24 is about 41% of the entire area of this curve. Or we say that's the probability that z is greater than 0.24, about a 41% chance. All right. Okay. Number 13, try that one now. Roll that into classwork number 1. Find the area between z equals 0 and z equals negative 2.19. So that's going to be this area here they want you to find. Or they want you to find this probability. There you go. Go ahead and do that.
Oh my God.
All right, so you're going to go grab normal CDF, and the lower end point is negative 2.19. The upper end point is 0. Mean is 0, standard deviation is 1. Hit enter, enter again, and you get about 0.4857. We get in that area about roughly in there. Or that's that probability, about 49% chance. Okay. We all get in this area here?
Yep.
All right, so we have a pretty good understanding now how to use this normal CDF function and what it can do for us. A normal CDF function always computes areas or probabilities underneath a normal distribution curve. All right, let's go down here. These are all just repeats. A whole bunch of practice here, repeats. Okay, no, hold on a second. All right, now, ladies and gentlemen, we're going to do something different. Now, they're not going to give you the z value on the horizontal axis. They're just going to give you the area, okay, of a shaded region. And they want you to determine what z value that has to be. So now we got to find out what z value above of which and below of which, below 0 of which lies this shaded area of 0.4175. So we're kind of like, you know, working backwards now. And, you know, I mean, how are we going to do that on our calculator here? All right. Well, the function that we're going to use is called the inverse norm function on our TI-84 calculator, inverse norm. The inverse norm function finds z values on the horizontal axis. The normal CDF function finds areas. Okay. So given an area, now we're going to have to use the inverse norm function to find the z value here. Now, this is the parameter list requirement for the inverse norm function. It must always be the area. This is the way the function works on our machine. It's always going to be the area, okay, to the left. It's always going to be the area to the left of a z value that we wish to find. Always has to be the area to the left of the z-value we wish to find, comma, the mean of the normal distribution, comma, the standard deviation of the normal distribution. It's got to be that argument list, okay? That's the way our calculator works. So, ladies and gentlemen, our calculator, this inverse norm function is not going to be able to find this area directly, okay? But I'm going to show you on your inverse norm function how we would. It's not going to find the z-value directly. I'm going to show you on your calculator how we can do this, okay? Remember, it's got to be an area always to the what? Left of a z-value. Okay, well, if that's the case, then think about it. What would be this area here to the left of my z-value? Think about the empirical rule and, you know, and the fact that the entire area underneath this entire curve must be 1, correct? So I have a question for you, ladies. What is the area of a normal distribution that is below the mean or the median or the mode? What would be the area that's below the mean of a normal distribution? It's always got to be what? What does the area of the lower half of the curve have to be? What do you think?
Negative?
No, areas are never negative because areas are probabilities. No, z-values can be negative, correct? To the left of 0, the z-values on the x-axis, on the horizontal axis are negative, and to the right of 0, they're positive. But probabilities are always positive. They're never negative. No, what was the area underneath the entire curve? You remember what it was for any normal distribution? The area underneath the entire normal distribution always must be what? 1, is that correct?
Yes.
1. Oh, Mitch, there you are. Son of a gun. You know, I've been seeing the name Mitch on when I'm doing attendance for Math 150, and for the life of me, I don't have a clue who it is. Who are you, Mitch? What's your last name?
French.
French? Okay.
Yeah. It's actually Steven.
Because I've been marking you absent. Son of a gun. I don't know, I don't know who Mitch is. So it's French, right? Or is it what, Steven or something? Or
Yeah, Steven French.
Steven French. All right, I'm going to have to go back and double check the attendance here and take care of that. I'm glad I got you. All right, I'll make a note of that so I won't mess that in the future there. Okay. All right. Anyways, ladies and gentlemen, the area, the lower half area of this curve, since the area of the entire curve is 1, what do you think the lower half area has to be? I think somebody said it. What was it? 0. What was it, Stephen? Do you say 0.5? 0.50?
Correct.
That's the area of the lower half of the curve. And the area of the upper half of the curve would also be 0.5. It has to be by symmetry. Because remember, this curve is perfectly symmetric. All right. So I have a question for you. How can I find my blue shaded area here? It's real simple to do. How do I find it? How do I find this area, this blue shaded area here? All I got to do is what? Take the what? 0.50 and subtract off what? Take the 0.50 and subtract off the 0.4175. That's all we got to do. We just have to do a little basic subtraction here. And we'll have the area to the left of the z-value that we seek. So what is 0.50 minus 0.4175? So what am I going to put in for that area to the left of the z-value I want to find here?
0.0825.
0.0825. That is the area to the left of the z-value that we want to find. Comma, the mean of this distribution is still 0 since it's still the standard normal distribution, and the standard deviation is still 1. That's how we're going to find that z-value. So let's go get our calculator now, and let's go see where this function hangs out. All right, let me move this over here and bring this over here. Okay. All right, ladies and gentlemen, to access the inverse norm function, we have to hit the second key. All right, we have to hit the second key followed by the vars key to get into distribution again. But this time we go down and grab the inverse norm function. Inverse norm. That always finds z values or values on the horizontal axis. So bring it up. The area to the left of the z value was 0.0825. Remember, it's always got to be to the left of the z value. That's the way this function's geared. The mean is 0 and the standard deviation is 1. Hit enter again, and that z value should be about negative 1.388. That's the z value. So that's what this value is equal to right here, is negative 1.388. Do we understand how we found that z value? So about 8% of the area of the entire curve lies below z equal to negative 1.388. Do we understand how we found that z value? All right. So remember, it's always the area to the left of the z value that we seek. Unfortunately, the calculator cannot compute this directly the way we see it in the book here, all right? So we had to do a little basic subtraction with our knowledge of symmetry and our knowledge of the fact that underneath the entire curve must be the area of 1. All right. That's not really a big deal to have to do that. All right, any questions on this, how we did that? So the normal CDF function does not work for problems like this. It works for problems like this, like 36 and 37, whereby we're given the z values on the horizontal axis and we're being asked to find the area within that interval. That's the normal CDF function. But when we're given the area, but not given the z value or z values, we have to use the inverse norm function. So there's a night and day difference between what's going on here. All right, so ladies and gentlemen, I want you to do problem number 42 for classwork 1. Roll it into classwork 1, number 42. I want you to find this z value here, between of which and 0 lies 0.4066 of the area of the entire curve. So you're going to have to use your inverse norm function. Go ahead and do that. I'm going to let you think about what area you have to type into the inverse norm function based on the last example I just worked out. Let's see if you can figure it out. Okay, so what is the area to the left of that Z value? Well, we know that the lower half of the curve, in other words, the area below Z equals 0, must be 50% of the area. So we just take 50%, 0.50, and add on 0.4066. That gives us the area below the Z value. So the total area below the Z value that we wish to find is 0.9066. Therefore, that goes in for the inverse norm function. And did anybody get that Z value? Now I got a question for you. Is this Z value going to be positive or negative when you get done finding it?
Positive.
It better be positive because it's to the right of, Z equals 0, the mean of the standard normal distribution. So it has to be positive. If it's not positive, that means that you made a mistake. What the? All right, so let's see if we can find it. Well, turn the calculator on. Second vars. Go down to inverse norm. The area to the left must be what did I say? 0.9066. I mean, mean and standard deviation is still the same. And that Z value should be about 1.32. Did we all get that there? 1.32. So that Z value should be about 1.32. Or that's about 1.32 standard deviations above the mean of 0, correct? So the area of the curve below this value of 1.32, Z equals 1.32, this entire area would be about 91% of the entire area of the of the whole curve. Okay. And that makes sense because you can see it's a large portion of this area here. Any questions how we're finding Z values using the inverse norm function on our calculator? All right. Okay, let's see. Anything else here? All right, let's see here. All right. I don't see. Okay, yeah, right here. Number 44. I want you to do this one right now. Find that Z value, ladies and gentlemen, above of which is only about 2% of the area of the entire curve. Number 44, roll it into classwork 1. Find that Z value. All right, ladies and gentlemen, so we're gonna apply the normal distribution to the so-called real world. Okay. We've already seen that areas are the same thing as probabilities, all right? Now, the only difference between this presentation and the one we just got done with is the fact that now we're going to deal with other normal distributions, not necessarily the standard normal distribution anymore. And in the old days, before we could compute probabilities underneath other normal distributions, we had to first of all standardize our observations to conform to the Z distribution, the standard normal distribution, of which we could then use tables in the back of the book that had probabilities for just the standard normal distribution. Well, we don't have to worry about that again, because we have our calculator. And our calculator can deal with any normal distribution. All we gotta do is just change the mean and the standard deviation to have our distribution conform to some other normal distribution instead of the standard normal distribution. So this standardization of these values here, these data values, is really not that critical anymore, but I'll show you kind of like what's going on here. If you look at this example, an average American household generates an average of 28 pounds of recyclable paper waste every month. Assume this amount is normally distributed with a standard deviation of 2 pounds. What is the probability that a randomly selected household is generating between 27 and 31 pounds of paper waste? So in other words, they really want us to compute this probability here, where X represents the weight of recyclable pounds of paper waste per month. We're really being asked to find this probability that X lies between 27 and 31. Now, this probability, ladies and gentlemen, we're trying to compute conforms to a normal distribution that is not the standard normal distribution. It's a normal distribution where the mean is 28 now. And the standard deviation is not 1, but 2. So that's going to be mu and lowercase sigma now for this normal distribution. But how would we do this in the old days before we had the TI-84 calculator? Because in the back of your book, they only have probabilities computed for the standard normal distribution, which is called a Z distribution. Well, ladies and gentlemen, in the old days, we would have to first of all standardize these endpoints of this interval so that we could compute the equivalent Z-scores of these endpoint values. We'd have to use this formula. So the Z-score that would correspond to the endpoint of 27 would be 27 minus the mean of our normal distribution, which is 28, divided by the standard deviation of 2. And that left endpoint would be negative, Z is equal to negative 0.5. So this probability is really equal to the probability that Z is greater than negative 0.5. And standardizing the right endpoint 31 by using the same formula, we get the Z-score for 31 to be 1.5. So my point is this: in the old days, before we had the calculator, we had to first of all standardize the endpoints of this interval for our normal distribution so that it conforms to the standard normal distribution. And then by going back in the book and using your Z table, you could compute this probability here. And this probability here would be equal to the one we were being asked to compute for our normal distribution. All right. Because this distribution pertains to the standard normal distribution now. The one where the mean is 0 and the standard deviation is 1. But those days are gone, ladies and gentlemen. We don't really have to do this anymore because our calculator will compute this probability for this normal distribution with a mean of 28 and a standard deviation of 2. In fact, let's go ahead and do that. You can see that we're about to compute this area here, this shaded area, between X equal to 27 pounds and X equals 31 pounds. So let's go on our calculator and bring up our normal CDF function, and let's compute that probability. Okay. See, I can probably do it up here. So normal CDF. Left end point is going to be 27. Upper end point is 31. The mean of this distribution is 28. The standard deviation is 2. And there you go, ladies and gentlemen. The probability is about 0.625. So there's about a 62% chance that if we randomly select one of these households, the monthly amount of paper waste that's discarded would be between 27 and 31 pounds. The probability of that occurring would be about a 62% chance. Okay. Now, I'm going to show you that the probability we computed is equal to the probability of the standard normal distribution if you're to standardize these endpoints. So I'm going to go back to bars distribution and grab the normal CDF function. And I'm going to type in negative 0.5. Whoops. For the lower endpoint, and the upper endpoint is positive 1.5. And this is for the standard normal distribution now. But notice we'll get the same probability that we got by computing with the endpoints of 27 to 31. Same area. Everybody see that there? Same probability. You see, in the old days, we had to do this because we did not have this calculator that could compute probabilities for this normal distribution with a mean of 28 and a standard deviation of 2. We always had to conform our normal probability to the standard normal probability distribution so we could use the tables in the back of our book. That's why this was important yesterday. But today it's unimportant. We don't need to standardize these values and, compute the equivalent z-scores for these values and then compute the z probability. We can just compute the normal probability of the distribution we were originally working with by using our normal CDF function in our calculator. So we live in a good time compared to yesterday as far as that's concerned. Everybody understand how we computed that probability there? And this is just showing you that this area here, ladies and gentlemen, for this normal distribution, the one we're working with a mean of 28 and a standard deviation of 2, is equivalent to this area underneath the standard normal distribution curve, where the endpoints are negative 0.5 and 1.5, because negative 0.5 indicates that 27 is a half standard deviation below the mean of 28 pounds for our normal distribution, and that 31 pounds of garbage is about 1.5 standard deviations above the mean of our normal distribution with a mean of 28. So we understand that these areas are identical, equivalent. All right. Now, here's a question. What is the probability that we randomly select a household and it generates more than 30.2 pounds of paper waste in a month? Well, that's going to be the area shaded to the left here that's above 30.2 pounds for our normal distribution, or equivalently, if you were to standardize 30.2, it would give you a z-score of 1.1. That would be equal to the area underneath the standard normal distribution that's above 1, z equals 1.1. All right, but again, we don't need to do the standardization. So let's bring up our calculator and just dial this up. So clear our screen, go get our our normal CDF function. My lower end point is what? 28? 28? No, not 28. Our lower end point is 30.2 pounds, correct? 30.2 pounds. Upper end point is positive infinity, which is simulated by using 10 to the 99th power. The mean of this distribution is 28 pounds of paper waste per month. The standard deviation is 2 pounds per month. Hit enter again. Boom, you got the probability. So there's about a 13.5% chance that when we randomly select a household, that household would produce more than 30.2 pounds of paper waste per month. Okay. That would be equal to the same probability if you were to use the standard normal probability distribution. That would be equal to the standard normal distribution where the lower end point would be 1.1 and the upper point would be positive infinity, where now the mean would be 0, the standard deviation would be 1 if this is a standard normal distribution. But I bet we get the same area. We do. Same probability, same area. Is this making sense here? All right. So again, you don't have to standardize your endpoints of your interval for your normal distribution to conform to the standard normal distribution. You don't have to do that anymore because we got the normal CDF function that can go to bat for us for any normal distribution, regardless of what its mean and standard deviation is. All right. Now, here's a situation, ladies and gentlemen, where suppose we're given the area or the probability of something, and we want to try to find, what the original X value was, or the original value of our random variable was. In that case, we would have to destandardize our z-score to bring it back to our X value that conforms to our normal probability distribution. But ladies and gentlemen, like I said, this is rendered obsolete too, because we have the TI-84 calculator with the inverse norm function that takes care of this business for us. So we don't have to worry about destandardization. Let's see if we can answer this question using our calculator. For example, to qualify for a police academy, candidates must score in the top 10% on a test. In other words, ladies and gentlemen, they must be in the what percentile to qualify? To say that your score is in the top 10% means that you are in what percentile bracket? How many what percentage of the scores are below yours if you're in the top 10%?
You're in the 90th percentile.
You're in the 90th percentile. So you have to score at least in the 90th percentile to qualify for this academy here. Assume the test scores are normally distributed with a mean of 200 and a standard deviation of 20. What is the lowest qualifying score? In other words, what's the lowest score you can get on this examination, ladies and gentlemen, and still qualify for this academy? We're going to find that out. Notice now they give us the area. The upper tail area is 10% of the area of the entire normal distribution curve. Furthermore, notice our normal distribution is with a mean of what? 200. That's mu, and its standard deviation is 20. To find this X value, we don't have to use a standard normal distribution and destandardize this value. That's old school. That's yesterday. But we got our calculator. We don't need to deal with that anymore. All we got to do is bring up our inverse norm function. Remember, inverse norm always finds values on a horizontal axis. It does not find probabilities or areas. The normal CDF finds areas or probabilities. All right, so inverse norm, we always need the area to the left of the value we seek. We need this area to the left. What would be this area to the left? What is all this area down here? Well, if the upper tail area is 10%, that means the lower tail area has to be what? The lower half of the area below X has to be what? 1 minus.
90.
Yeah, it has to be 90%. So that's the area we type into the inverse norm function is 0.9. Because you always need the area to the left of the value you find, whether it's a z value or just a normal X variate for some other normal distribution. So this is 0.90 or 0.9. The mean of this distribution is 200, comma, the standard deviation is 20. All right, let's find out what that minimum score must be in order to qualify for this, this academy here. So we're going to find out now. So to do that, we bring up our inverse norm function. We type in the area to the left of the X value we seek, which is 0.90. The mean of these exam scores was 200, and the standard deviation score of all these exam scores was 20. Here you go. The minimum score, ladies and gentlemen, that you must attain on this exam must be 225.6. I got a question for you. Do you think they would round this value up to 226 or down to 225? Think about it. What do you think, Lizzo? In this situation? For qualification purposes. Now, for qualification purposes, yeah, they're probably going to round it up to 226 because they want to make sure that you surely qualify for this academy. They're not going to round it down. It's skimp. They're probably going to round it up to 226. So yeah, you would probably have to score at least a 226 on this exam to even qualify. Anything less, you're out. Okay, make sense? All right. So that's finding an X value on our horizontal axis, given the probability of some event. Okay. Again, we use the inverse norm function, always find values on the horizontal axis. The normal CDF always finds probabilities. This is just showing you from your table how to go about all this. We don't need to deal with that though. Okay. All right, here's an interesting one. A researcher wants to select people in the middle 60% of the population based on blood pressure. Blood pressure is normally distributed with a mean of 120 and a standard deviation of 8. I don't know what the units are. It could be millimeters of mercury, or is blood pressure normally millimeters of mercury? Any nurses out there or health people? Millimeters of mercury? I don't know. I think I've seen that in the health field where it's millimeters of mercury. I could be wrong. Now, if X sub 2 and X sub 1 are the bounds of the middle 60%, then 20% of the population must be less than what? X sub 2. How did they get that, Lizzo? They're using what? The empirical rule and symmetry. Because look at, we know that we want to select the middle 60% blood pressure readings. So 60% of our blood pressure readings lie between X sub 2 and X sub 1. That leaves 40% of the area of the rest of the curve to lie equally in the lower tail down here and also the upper tail up here. So therefore, we're going to turn it over to our inverse norm function on our calculator. And if I want to find X sub 2, what am I going to type in for the area to the left of X sub 2? What am I going to type in here? What's this area to the left of X sub 2? It's 20%, correct? 60% is in the middle. That leaves 40% equally allocated for the lower and upper tails. So 40% divided by 2 leaves 20% of the lower tail area. So we're going to type in 0.2. The mean of these blood pressure readings is 120. And notice these blood pressure readings are normally distributed. And the standard deviation is 8. Get on your calculator, dial it up, and tell me what this lower endpoint value X sub 2 would have to be equal to. So what would have to be this lower blood pressure reading of this interval? I think they get about 113.28. Is that correct?
113.27.
Okay. That would be the lower endpoint value. Then you want to find X sub 1. How could we do that? There's many ways to do that because we have perfect symmetry here. One way to do this, ladies and gentlemen, is to determine how much area would be to the left of X sub 1. Well, we know that 30% of the area is between what? Here and here. Do you agree? By symmetry. And then you just got to add what? An extra 50%, the lower area, the lower half area of the curve. So that's 80% of the area that's less than X sub 1. So therefore, we would type in inverse norm. We go get inverse norm. And we would type in 80% of the area is less than X sub 1. The mean is still 120. The standard deviation of these blood pressure readings is still 8. Dial that up, and you should get about 126.72. So therefore, we would expect that 60% of blood pressure readings from the entire populace to lie between 113.28 and 126.72. And again, I'm assuming this might be like millimeters of mercury. Okay, there you go. Another way of looking at this is this way. If I was to randomly select a person from the populace, okay, what is the probability that their blood pressure would be between 113.28, 126.72 millimeters of mercury? That'd be a 60% chance. So what's the probability of selecting somebody and their blood pressure exceeding 126.72? You would say the probability would be what? 20% chance. Was the probability of randomly selecting somebody and their blood pressure being less than 113.28? You would say 20% chance. Is this making sense here? Okay. This is a crude test for normality. Ladies and gentlemen, I've never really worked with this much. In all honesty, I've never really seen it in any other textbooks other than this one. I don't know why it's here, but it's called the Pearson coefficient of skewness. I don't know if I'm gonna even assign problems with regard to this, but basically the way it works is this: if you have a data set and you compute the mean and the median and the standard deviation of that data set, and you put those values into this formula here, if this coefficient lies between 1 and -1, then we would accept our data as being approximately normally distributed. If this coefficient is greater than 1 or less than -1, then we would say that our data is skewed, okay? That's one way to test for normality, is by computing this Pearson coefficient of skewness, all right? There are other ways to compute normality. Another way to compute normality of how normal your data set is. Well, you can see right here, they give you an example here. Here's a data set, and they build a histogram for the data set, which looks, I don't know, maybe a little bit bell-shaped, but it doesn't really look that great for symmetric, you know. And then they compute the mean and the median, standard deviation, and then they throw it into this Pearson correlation coefficient here, and it gives you like 0.148. Notice 0.148 is definitely between 1 and -1. So, you know, according to this, it has passed the test for normality. All right. All right. And here they're checking for outliers, where remember a data point is considered to be an outlier if it's more than 1.5 times the interquartile range less than your first quartile, or 1.5 times your interquartile range greater than your third quartile. Your data point is considered to be an outlier. All right. Now, another method for testing for normality is to construct what's called a quantile plot. A quantile plot is like a percentile, but not expressed as a percentage. Basically, a quantile plot determines the percentile or quantile of every data value in a data set, then calculates the equivalent z-scores of the values and determines the percentiles of those values in the normal distribution. If each value is roughly the same percentile as its z-score, the distribution is approximately normal. So what does all this mean here? Well, how can we construct a quantile plot here? Well, we can on our calculator. You go into your stat plot mode, and notice it's going to be this last icon here, which is a quantile plot, all right? And bottom line is this: when you build a quantile plot for a list of data, which was like put maybe list 1 here, okay? And you have to specify, let's see here, make sure the data is in list 1 and X is highlighted for the data axis. Okay, so you want to select for the data axis, you want it to be the x-axis always. Just always select the x-axis. The bottom line is this: when you build this quantile plot, all right, if these points appear to lie on a line, if they lie on a line or are very close to lying on a line, then we would say our data set is normally distributed and symmetric. Okay? If these data points are all over the joint, all over the place, then you would say that your data set is not normally distributed. All right. So the closer these points for a quantile plot lie on a line, the greater argument there is for your data set of being normally distributed. That's how a quantile plot works. So like if we had a data set, could we do a quantile plot for this data set here? Do you think that might be possible? Well, we could maybe try. Let's see if we can just throw this data in a list and try it out. Okay, so I'm gonna try to put this data in a list here. So stat edit, list one. We're gonna try this out here. $63, 113, 68, 118, 74, 151, 70. Whoops. Hold on. 74 and 158. I think I have an error on one of my data points up here too. It should be 44. I think I typed in 4. Yeah, this should be 44. All right, let's see if we can build a quantile plot. Second mode to quit. We enter the data in list one. Let's go to the stat plot. Second y equals. Turn plot one on. Go navigate your blinking cursor till you get to the quantile plot, which is the very last icon. Hit enter. We want the data axis to be the x-axis. The data list is list one, and we're ready to do this, ladies and gentlemen. It's that simple. So we've basically configured plot one to build a quantile plot. Let's just go to zoom stat, and away we go. All right. So you can see that, ladies and gentlemen, these points tend to lie on a line for the most part. Not exactly. I mean, they tend to get further from the line the further we go to the right. These data points kind of stray away from the line a little bit. You can see that. But for the most part, most of the points are hugging the line. And for that reason, we would classify this as being what? Approximately a normal data set. Okay. Approximately normally distributed. That makes sense? That's the quantile plot. All right. So I don't know. I mean, I might ask you a question with the quantile plot. That's how you build one on your calculator. Maybe with Alex, maybe I'll give you a problem with the quantile plot. It's really pretty simple to build, as you're finding out here. Just remember, the closer these points all lie on a line, the greater the argument is for your data to be normally distributed. If these points are kind of like haphazard and lie, you know, in a random fashion, not really lining up on any line, then your data set is probably not normally distributed. Okay? Quantile plot. All right. Now, we don't really have too much time left as far as practice problems are concerned. And in fact, but in section 6.2 are applications of the normal distribution, where they will have you, you know, working with the normal distribution and computing some probabilities here. What I might do is, let me take a quick look at the schedule. 150. All right. Let's see. I'm like pretty much out of time here today. 6.3, the central limit there. Okay. Well, maybe what I'll do is I'll make maybe like a little supplementary video, as I'm working a couple problems out of 6.2, some application problems. And I'll demonstrate them on the calculator. And I'll just attach that video to Canvas for your viewing, okay? So, sorry, I ran out of time today. Not really enough time to do any, or to dig into any of these wonderful application problems. But the normal distribution can be applied to, you know, a lot of problems that have data that are normally distributed. Okay. And like I said, you're welcome to look down through the section at some of the examples that are in here. And like I said, I'll try to do a couple of these, work out a couple of these problems here. Try to show you one of each type. I mean, I'll try to show you how we're computing probabilities, and I'll try to show you how we're finding, you know, the X values. So I'll show you problems that warrant the use of the normal CDF function and those that warrant the use of the inverse norm function. All right. I'll show you some good examples there. All right. Well, you guys have a good night. And if you have any lingering questions or concerns, I'll be on the line for a couple minutes. If not, take care. And just remember the due dates for the Chapter 5 quiz and the Chapter 5 exam, and also the homework. All right. I'll see you.